sometimes when we have a correlation, a linear model might not be the best model to use. An exponential model might be a better fit. So if I've got two variables, x and y, and they don't make a straight line, instead we see a curve, then an exponential model might be a better fit. And there are two different ones we're going to look at. So we could either have x against log y, or we could have log x against log y. So when we change it to an exponential model, we might get a better fit for our data, and then it'll be a more useful regression line, a more useful model to use. So in this first example, data are coded using y equals log a and x equals log b. So we're coding the data to change them to logs. The equation of the regression line is found to be y equals 0.8 plus 1.2x. Given that the data can be modeled by an equation in the form a equals kb to the power of n, where k and n are constants, find the values of k and n. So in this situation, we had two variables a and b, and we've coded them to change them to x and y, and we've found they've got a straight line relationship between x and y. And now we want to change it back into a and b. So y is log a, so we're going to change y into log a, and x is log b, so we're going to change x into log b. Now we want to get rid of these logs. So the 1.2 in front of log b, when we've got something timesing by a log, we can pull the 1.2, in this case, up and make it a power. So log a equals 0.8 plus log b to the power of 1.2. I'm now going to get my logs on the same side. So I'm going to take away my log b to the power of 1.2. So log a minus log b to the power of 1.2 equals 0.8. When I've got a minus between two logs, I can change it to a divide. So I've got log a over b to the power of 1.2 equals 0.8. I'm now going to get rid of the logs. So this is log base 10. To take it out of log form, if you remember, it's just the same as 2 cubed to the power of 8. Log base to 8 equals 3. So we're just going to take it out of the log form. So we're going to have 10 to the power of 0.8. So the base, the power, equals a over b to the power of 1.2. And we want to get it a equals, so multiply by b to the power of 1.2. A equals 10 to the power of 0.8 times b to the power of 1.2. I'm going to change 10 to the power of 0.8 to a number. 10 to the power of 0.8 is 6.31. So I'm going to say a is 6.31, b to the power of 1.2. So k is 6.31 and n is 1.2. Okay, one for you to try. See if you can give it a go. So again, it's the same question. A and b have been coded to give y and x, and we've got a straight line relationship between y and x. We need to find the equation in a form a equals k b to the power of n, where k and n are constants. So y is the same as log a, and x is the same as log b. The 2.1 can jump up and become a power. So log a equals 1.4 plus log b to the power of 2.1. Get the logs on the same side. So log a minus log b to the power of 2.1 equals 1.4. A minus in logs means divide. So log a over b to the power of 2.1 equals 1.4. Take it out of log form. So 10 is the base, 1.4 is the power, and the answer is a over b to the power of 2.1. Multiply by b to the power of 2.1. So we have a equals 10 to the power of 1.4 times b to the power of 2.1 10 to the power of 1.4 I can write as 25.1. So a equals 25.1 times b to the power of 2.1. So that makes k 25.1 and n 2.1. Here's another question. The time in months t and the number of ants in a population are recorded. The data is coded using y equals log p and x equals t, and it is found a linear relationship exists between x and y. The equation of the regression line is y equals 2.4 plus 0.041x. Find an equation to link t and p in the form p equals a b to the power of t, where a and b are constants. So y is the same as log p, and x is the same as t. So we want to take it out of log form. So 10 is the base, all of that is the power, and p is the answer. So p equals 10 to the power of 2.4 plus 0.041t. When we multiply indices, we add the powers. So that's the same as 10 to the power of 2.4 times 10 to the power of 0.041t. And we want ab to the power of t. So I'm going to rewrite that again as 10 to the power of 2.4 times 10 to the power of 0.041 to the power of t. So a is 10 to the power of 2.4 and b is 10 to the power of 0.041. So we just need to find out what they are. 10 to the power of 2.4 is 251. So a is 251. And b is 10 to the power of 0.041, which is 1.10. Okay, one for you to try. See if you can give it a go. So the time in months t and the number of rabbits in a population are recorded. The data's coded, so y equals log p, x equals t, and we've got a linear relationship between x and y, and it's y equals 1.75 plus 0.255x. So we're going to change y into log p and change x into t. Take it out of log form, so p equals 10 to the power of 1.75 plus 0.255t. We're going to change that to two powers of 10 multiplied together. So 10 to the power of 1.75 times 10 to the power of 0.255t. And that's the same as 10 to the power of 1.75 times 10 to the power of 0.255 to the power of t. So 10 to the power of 1.75 is A, which is 56.2. I'm going to call that 56 actually, because that will be the initial population. I don't want to make it a decimal. And B is 10 to the power of 0.255, which is 1.80.